So let's get a similar brief introduction to the ocean component of climate models and ocean modeling and ocean's role in climate. Obviously, we already said that ocean is deep, has high heat capacity, warms slowly, cools slowly, has all the memory, and you can think of sun being in one hemisphere for 6 months and the other hemisphere for the other 6 months. So the ocean is soaking up the heat during that time and then giving it up at various time scales. So ocean theoretically can generate literally very, very long time scales, especially when we consider the thermohaline circulation. So as a schematic, we said that ocean is forced mostly from the top. There are some geothermal heating, which is insignificant in terms of generating any circulation features of any significance. Of course, there are tides sloshing around and generating waves as they hit the mountains in the ocean, and those waves break and create mixing, and they are very important. And it's also been argued that the animals that move up and down and live in the ocean can produce enough kinetic energy and heat to have a mixing effect, but we will not worry about that right now. So looking at a schematic, the view of the ocean shows a mixed layer like the boundary layer in the atmosphere, and the pycnocline, or the sharp density gradient, or the thermocline, which is the sharp temperature gradient. You can look up these in my other podcasts. In fact, I have a whole section on ocean's role in climate under physical oceanography and climate, where a lot of these details will be are discussed. But here it's just focused on the modeling. Deep ocean is shown below here. Changes of salinity are red when it's important enough. Changes in water are blue here, and evaporation is shown here. So red as well. So evaporation, precipitation, runoff, and changes in energy radiation are shown in green here. What else? Ocean motions are in black and include wind stress, surface currents, downwelling and upwelling in the deep ocean. Again, ocean models also can be various complexities, just like the atmospheric model. So like the atmosphere has clouds and a hydrologic cycle, ocean has salinity and a hydrologic cycle. Of course, there are also phytoplankton, which can act as clouds in the sense of affecting the penetration of solar radiation into the ocean and impacts on heat budgets and circulation. So oceans receive salinity perturbations and freshwater perturbations at the coast, but in general in the open ocean over millions of years of time scale, salinity is basically a conservative quantity, except near the surface where there is evaporation and precipitation. So as a whole it is conservative. Surface fluxes again include sensible, latent, long wave, and solar radiation. Wind stresses give kinetic energy to mix the colder waters into the surface warmer layers, so you can see the salinity perturbations there. Radiation, of course, depending on how clear the waters are, shortwave can penetrate deeper, and we have long wave, which is not as significant. So shortwave and latent heat flux, so evaporation, are the major balances. Precipitation doesn't do much other than add freshwater perturbation. And of course there are sea ice, which are very critical in two ways. One, when ice forms, the brine rejection happens, so salt is left behind, water can get heavy and sink and cause mixing and bring new water, so the ocean never grows very thick sea ice unless it's confined water like a lake, for example. Otherwise this circulation generated by brine rejection always brings in new water, means new heat, so the sea ice never gets very thick. But the other impact is that it insulates the ocean surface, so heat loss from an open ocean can be orders of magnitude higher than the heat loss here, because sea ice is a very good insulator. And the deep ocean circulation is set by the so-called thermohaline processes, which we have looked at elsewhere. So at high latitudes in the North Atlantic and Labrador Sea, so Greenland, Iceland, Norwegian Sea, and Labrador Sea, and in the Southern Ocean in Weddell Sea and Ross Sea, there are processes like sea ice formation, heat loss, evaporation, etc., that form deep water which sink below the Pinnock line and set the deep ocean in motion. But this motion is so slow that you cannot even measure it directly. You have to use tracers to infer motion. Of course, currents are small doesn't mean transports are small, because transport is integrated over a volume, so transport can still be large. But nonetheless, this time scale of deep motion is very slow, hundreds to many hundreds of years, more than 1,000 years, for example. So there are fast time scales near the surface, slower time scales below the surface, but the thing to remember is that when the water does sink in certain places, it can take heat and greenhouse gases with it, and oxygen as well. So ocean hides away through various processes over 93% of the excess energy generated by human activities and increased greenhouse gas trapping of additional solar radiation or outgoing long-wave radiation. So here is an example of an ocean basin, representation of an ocean basin from the equator to a northern boundary. Trade winds near the equator in red and westerlies away from the equator cause water to move along and away from the equator because of the Coriolis and tilting of the Thermocline or Pinnock line. The motion of water away from the equator causes upwelling. So if you have the winds blowing this way, what is being shown here? This figure is really not such a great figure, right? So it is showing a equator to northern basin, so presumably winds are blowing this way, which means there is going to be divergence on this side, which is actually, I think I turned it around because trade winds have to go the other way. Anyway, you know how it should work. So there should be upwelling, which means Thermocline has to be raised over here, and as the waters are pushed towards the west, let's say this is the east and that's the west, so the equator and that's the north, then Thermocline actually should be shallower here and deeper over there. So whatever the hell this figure is, this is not very sensible, so I'm going to leave it there. Deep ocean circulation, as I said, there is North Atlantic deep water forming here in the Jin Seas and Labrador Sea, and there are Antarctic bottom water and Antarctic intermediate water being formed in the Southern Ocean. So the blue waters here sinking and moving south. We have discussed elsewhere about why there is western boundary intensification of these pathways, and the water mixes in the Southern Ocean and inundates the Indian and Pacific Oceans. It's seen here as blue and purplish lines, and eventually upwells and comes back through the Indonesian seas, mixes with the water that's going into the Indian Ocean below the surface, converting to surface water, coming back. Both are mixing together. Some of it is retroflecting back, some of it is crossing over and crossing the equator into the region. Basically, if you're sinking water here, you have to replace it with water coming from elsewhere. So this is the water that comes back and resupplies the sinking part. So this is the thermohaline circulation. So the red lines here are warm surface currents, and blue lines are the cold, deeper waters. So it could be North Atlantic deep water, Antarctic bottom water, Antarctic intermediate water, and so on. And of course this is very small basin, so the overturning circulation here is much shorter in time scale than over here, but the water that sinks here, mixes here, and goes and comes back takes hundreds of years to thousands of years. Okay, so this is an important process of how the anthropogenic warming and generally climate variability are moderated and modulated by the ocean circulation. Ocean is full of eddies. We have seen elsewhere this ocean in constant motion, a NASA video of model simulations, and this is the Gulf Stream, which shows the eddies. So as the Gulf Stream meanders, you have cold core eddies on this side, warm core eddies on the other side, observed in the the infrared temperature maps from the satellite, and there is always a debate about whether these eddies are contributing to the net heat transport across, let's say, a latitude line. That debate continues, but ocean is full of eddies, and some models try to resolve those eddies. Then there is a resolution issue. If you want to capture such small scale features, the resolution of the model has to be high enough, because it's related to the so-called Rossby radius of deformation, which determines the size of the eddies in terms of the balance between stratification and rotation. So details which you will have to look up elsewhere in the other podcasts. So surface ocean has lots of complicated processes of heat exchange, gas exchange, water exchange near the surface, and upwelling. So if you are looking at the California coast, there is the California upwelling, which is full of phytoplankton and fish. So surface winds can diverge water based on Coriolis. Remember, in the northern hemisphere, Coriolis tilts the currents to the right of the direction of motion. So surface water motion, if the winds are blowing this way, then surface waters will be tilted to the right of the winds, which can give you divergence, so water moving away from the coast, which means cold waters being pulled up from below, and usually that means nutrients coming up, cold water, nutrients, phytoplankton, fish, and so on. Okay. Finally, sea ice is a key process at high latitudes, and Arctic sea ice loss is being constantly discussed now. Even in the Southern Ocean, there are complicated processes by which there is a decadal increase in sea ice, for example, which is argued to be forced from the tropics because of the teleconnections through the atmosphere. Nonetheless, sea ice is a key process, and sea ice model at the surface includes winds, radiation, open areas between ice where heat loss can be orders of magnitude larger than where sea ice is present, snow on ice, and melt ponds. So if there is snow on ice, albedo can be very high, especially if it's fresh white snow. Key processes at the base include currents, growth, melt, and brine pockets. So sea ice modeling is quite advanced now, and most models have a sea ice model. Land ice is another issue. Very few models still have a full-blown glacier model, which will continue to improve, I'm sure. So winds blow around the sea ice. So typically sea ice forms. It can have melt ponds where top of the sea ice is melting because of the radiative heating, and then albedo increases, more energy is trapped, so the melt ponds can grow. There can be ridging, there can be snow on top, and currents can drift sea ice, especially shelf ice, which is not sea ice. Different processes. So brine pockets can form when sea ice forms. Ice rejects salt, so those processes can happen, and these kind of ice formation, brine rejection, and so on can set up local convection and mixing, and so on and so forth. So these are all key processes which models are nowadays able to account for. And the key processes being looked at under global warming is, of course, how the tropical Pacific responds. If you remember the climatological state, Eastern Pacific has upwelling and cold temperatures, Western Pacific has warm temperatures. Cold upwelled waters soak up heat from the atmosphere like a sponge. So under global warming, if the East Pacific warms less than the warm West Pacific, then the ocean will continue to support east-west sea surface temperature gradient, pressure gradient, strengthening of the trade winds, and continued upwelling, and hence ocean uptake of heat will continue. And this has been argued to be the case for 1998 to 2012 or so, when there was an apparent slowdown in global warming, and it's argued that the cold Eastern Pacific continued to soak up the heat and take away the additional energy and moderate the heating of the atmosphere, the global warming, and some of that water, the heat was pushed into the Indian Ocean through the Indonesian seas because of the stronger trade winds and so on. So ocean has a huge role to play in global warming. Ocean models are obviously obviously doing a good job of representing many of these. And then there is a question of how the meridional overturning circulation changes because of global warming, and this is not completely understood yet, but there are already papers arguing that the Atlantic meridional overturning circulation is the weakest it has been in 20,000 years, which means going to the end of the last ice age, when last glacial maximum happened around 21,000 years ago, and then the ice started melting. So those kind of issues are important, because those are very critical for how much heat is being taken up by the ocean and so on. So when oceans and atmospheres get coupled, we will have other issues to worry about, which we will do in the next chapter. Okay, very brief introductions, a lot of words, but as I said, without equations I can only give you words, but you have to read the book, which has many more details, and I'm just summarizing it here very briefly, so please read up if you are interested in more. Okay.